Okay, here's a free body diagram that class constructed for the bracket situation we saw before. You've got a bracket, that's this thing. You've got a weight here. You've got an elastic cord here. Okay, stretched out, and the bracket is pulled back a little bit, so it's above, so it's at an angle with the horizontal tabletop, and we have a weight on the end of the bracket here. The bracket's in contact, obviously, at this vertex here. So we do a diagram. Okay, well, people listed a few forces that would be considered internal to the system if the system is going to be regarded as the bracket itself. Okay, with the weight on it, bracket and weight. So there's a frictional force that keeps this thing from sliding down, but that's internal to the system. And there's a normal force here. It's also internal to the system. And these forces don't exert torques. They don't influence the acceleration of the system if it happens to be moving, or the other forces that we listed here. Also, there was an M3G. Now, M3 corresponds to the mass of the bracket. And that was originally listed here at the vertex, which is kind of where you think of the force being concentrated. But really, you put this force, the force of gravity, on the entire bracket at the center of mass of the bracket, which will be somewhere between here and here. So it's going to be a little closer here. You got a lot of mass here, and mass distributed here. So we just arbitrarily kind of put it right here, without even trying to estimate it. We can easily calculate the center of mass of the bracket. Just get the mass of the bracket and have equal masses here and here, and go from there. Okay, so that's good. We have an MG here. Now, actually, if we regard this as part of the system, then we don't have this M4G. Okay, so if we, in other words, account for this by calculating the center of mass of the bracket along with this mass, then we can get rid of this because its mass will be incorporated in the mass of the bracket system. But we can list it separately as well. And of course, if we regard it as part of this system, it's going to move the center of mass that way. So the center of mass might be out here if we don't include this M4G. So we're going to go ahead and include the M4G because that's the way it was drawn, and that's a valid way to do it. Again, the alternative is calculate the center of mass with a bracket plus this mass, and find the center mass and concentrate the total mass of the bracket in this way at that point. Okay, so the force that got, okay, those are vertical forces. You also have a small magnet up here. It's clamping the elastic band to the bracket. And that magnet has a mass, so we'll call that M3G. That could also be included in the bracket system, take account of the center of that mass and so forth. But it can be listed separately, and I kind of like listing it separately for illustration. Angles are all labeled. Now, angles were labeled, both angles were labeled theta, all the masses were labeled M, so I just threw in subscripts. And they might be hard to read, but this is M1G, M1 being the mass of this 1 kilogram weight, 1 kilogram, mass of a 1 kilogram mass. And M2 being the mass of that magnet, almost called it a domino, I don't know why I keep doing that. M3 being the mass of, we'll say just the bracket without the attached weight here and magnet here, and M4G being this. Okay. Horizontal forces, there are really only two forces that appear horizontally. One is the horizontal component of the tension. Okay. Now, if we're regarding the bracket plus the two masses as our system, then the tension acts on that system here at this point in this direction. The horizontal component of the tension, of course, tends to pull the system this way. And if this is on a low friction surface, that would accelerate the system in the direction of the tension, of the horizontal component of the tension. Since there's friction, well, it's a frictional force here that resists that force. And if we pull hard enough, we might actually get this thing to slide. But that's not happening right now. It's sitting right there, just as we saw it in the video from the other day. Okay, so that's pretty much a list of our forces. And then I say, well, here are your conditions of equilibrium. Where do you want to do the torque about? And the class chose this point, same point I would have chosen. You could do it about any point, but the thing about this point is probably the most convenient and the most conceptually obvious. Okay. Now, ask the class to list the forces, to write this condition. And astutely, the class said, well, positive direction this way, then the tension force here is a horizontal component of negative T sine theta 1. Okay. And force of friction, which is acting in the opposite direction, the positive direction. So that's very good. Then positive is up. A little hard to read that symbol. That's what it means, positive up. In that case, the tension times the cosine of theta 1 is going to give us a negative. The y component of this tension is in the downward direction. If upward is positive, then it's negative. Okay, so we have that component of this tension. Then we have M2G, obviously, M2 being the mass of this, and M2G being the force exerted by gravity. And then we have the normal force at this point. And we have M3G, which is down, and M4G, which is also down, so that should have been negative. You can fix that easily. And all that equals 0. A little hard to read this, but that's what it says. Okay. Then the sum of the torques about point A. Well, this tension exerts a force at this point. If you multiply the horizontal component of that force by the moment arm, you get tension times distance, okay? And actually, we want to say just a little more about this. We aren't totally clear on what we mean by D. If D is the distance to the line of force of the tension from here, okay, well, if this isn't the right angle, then that line of force is maybe going to be, I'm sorry, the perpendicular line of force might be this way. Okay, so your moment arm would be this distance. And otherwise, you can say, well, if we know all these angles, then I can figure out what the angle is between here and here and multiply the tension times the sine of this angle and multiply it by the length of this part of the graph to get this. But that can be done. It's represented here without the full detail of these distances, which we haven't measured, and the angles, which we haven't measured. Okay, then we have M2G times D. Now, what are we using for D this time? Here's M2G, it's acting down this way. Moment arm would be from here to here. perpendicular to the line of force. One way to do it. Another way is to take this distance and then multiply this force by the sine of this angle here. Then take the product of those two things. So if we're doing M2G times D, though, the D would be the distance from the point of rotation to the line of force. Okay, M3G times, that's another D. Again, is use this distance times the M3G, or we could use this distance times M3G times the sine of this angle here. You want to understand it both ways. You'll be able to visualize it both ways. And then similarly with M4G, the same thing. We could, if we know theta 2 and this distance, we can calculate this distance here, okay, and multiply it by the M4G. If we know this angle, then we know this angle, and we can take this distance times mg times the sine of this angle, and we would get the same result. Okay, so again, this is a very good attempt. This is a very good exercise. If they came up very successfully, everybody in class seemed to understand quite well what was going on here. Devil's in the details, and the details would have to be worked out to totally reconcile everything. Pretty good picture. Now the elastic, excuse me, elastic band in the previous free body diagram. Well, there's the band. Okay. Now you notice if I stretch this band out, the whole band gets longer, and these two paper clips get further apart. Now, if I measure distance between the two paper clips, it might change by a couple of centimeters. So let's say the initial distance is 16 centimeters, say 18 centimeters, because that's what we're going to use here. And we change the length by 2 centimeters. Or we change the spacing between them by 2 centimeters. Now, the whole band is twice as long. The length of the whole band is double the distance between these two bands. So with the same force, the whole elastic band stretches twice as much. So if the distance between the paper clips increases by 2 centimeters, the length of this whole band increases by 4 centimeters. Still exerts the same tension, because if you ignore the weight of the rubber band, or the weight of the elastic band and the weight of the paper clips, which are fairly negligible, the tension through the whole elastic band is constant at any length. Well, this leads us to the idea that the tension is governed by the percent change in the length of the rubber band or the elastic band, or the separation between any 2 points on the elastic band. The ratio of the change in length to the separation of 2 points is the same for the whole band or for any 2 points within the band. So tension is governed by the, let's say, the percent change in the length of this elastic band. The elastic band has a cross-sectional area of 6 square centimeters, approximately, as I measured it. So we'll assume the cross-sectional area is 6 square centimeters. If I had 2 of these together and stretch them out, then I get twice the force. So it's a fairly simple step from that idea to the idea that the amount of force exerted by the band is proportional to the cross-sectional area of the band. Okay, so we have that proportion. Well, using these ideas, you say, well, if we stretch the rubber band or the elastic band, an 18 centimeter elastic band, 6 additional centimeters, then what can we say about what governs the tension? Okay, well, this means that we've increased its length by 33%. Okay, so we have a 33% or a 0.33 factor increase in length. Tension, let's say, is 20 newtons. And the cross-sectional area is 10 square centimeters. Okay, we define stress to be the tension per unit of area. Now that's a unit of cross-sectional area. Let's say for unit of CS standing for cross-sectional area. Okay. Strain is how much its length changes. Okay. And actually, we're going to say strain is percent of stretch. Okay, so in this case, the strain of this thing would be 0.33 or 33%. Question now is what constant number tells you how the material behaves when stretched. So we could use the number to find the force of a 3 meter length of the same material, cross-sectional area 4 square centimeters as opposed to the 10 square millimeters. And if it's stretched 20 centimeters. Okay, well, we want to come down to what's the property of this material. And what we can think of is that the cross-sectional area determines how much tension. And the material, of course, determines how much tension. And the percent change in its length determines the tension. Okay. Or the percent change between and distance between any 2 points on the elastic band in this case. Well, class worked on this for a while, came up with the idea that maybe the stress on this thing is the tension per unit area. So the stress came out to be 2 newtons per square centimeter. How do we get that? We divide the 20 newtons by the 10 square millimeters. That's square millimeters, not square centimeters. Okay. 20 newtons divided by 10 square millimeters gives us our stress. The amount of tension we get per unit of area. The strain was our 33% or 0.33. And then there was an attempt made to put these together and say, okay, if I multiply this by this, let's say 2 newtons per millimeter squared times 0.33 equals 0.67. This is 33 repeating. Newtons per millimeter squared. Big question mark. Is this right? Well, I pointed out that this is a property of the material. It's not going to change. So if I increase, let's say that 33%, of course that elastic material won't stand a 33% strain. That's okay. Okay, well, if we have a material that would, if I increase this, that's going to increase this, right? So if this times this is constant, increasing this though would have to decrease this. If this gets bigger, this would have to get smaller. If this is a property of the material, it's always the same for the same material. So this can't be right. Or you would say, well, this times this has to equal this, so the stress times the strain has to equal this. So if the stress is doubled, you'd have to have half the strain. That means you apply twice the force, and you'd only get half the change in length. So that's just not right. So, well, people pretty clearly then, okay, that's not right, that doesn't work. And pretty much came to the conclusion that, well, it has to be the ratio of these two things has to be constant. Okay, so we could do the 0.33 over the 2 newtons per millimeter. Okay, we get 0.165 square millimeter per newton, or we could do the 2 newtons per millimeter divided by the 0.33 and get 6 newtons per millimeter squared. So you follow the work I see here. Okay. Oh no, they say, okay, you divide the stress by the strain, and you get 6 newtons per millimeter squared. And of course, stress divided by strain is a definition of Young's modulus. And we came to this just by reasoning a couple of false dead ends, like this one. But we came to this conclusion without having to actually define it. Well, we get this constant, and now the question becomes, how do you calculate for a 3 meter length of the same material, cross-sectional area 4 square centimeters, stretched 20 centimeters? Now, there's a way to just reason this out by proportionality. A 3 meter length is approximately 16 times the 18 centimeter length, okay? So since this is like 16 times as long, you would expect that you would only get 1/16 the force for a given change in length. Okay. Cross-sectional area is 4 square centimeters. Now 4 square centimeters is way bigger than 10 square millimeters. A square centimeter is 100 square millimeters. Just divide up a square centimeter into 10 parts this way, 10 parts this way, that would be a millimeter, and you get 100 square millimeters. So there's that picture. And of course, you can do this by centimeter squared is 10 millimeters squared, which is 100 millimeters squared. So you just do the form the unit calculation. And other ways that can be written out. Well, okay. So you've got like 40 times the cross-sectional area. Now that's going to give you 40 times the force for a given change in length. Okay, so a given change in length, another way of saying what happens to a given change in length, if you have the same change in length here as you have here, you would have only about 1/16 the strain, because you would be changing by only 1/16 as much of the original length. You want to think about that. Okay, well, due to the cross-sectional area being 40 times greater, okay, 400 square millimeters versus 10 square millimeters, all other things being equal, you'd expect this thicker band, or cord, whatever, to exert 40 times the amount of force that's given if everything else is the same. Okay. And I don't have room to write out all the ideas. Talking about the proportionalities, again, you have 40 times cross-sectional area. That alone would tend to give you 40 times the force, 40 times the tension. 3 meter lengths would tend to give you like 1/16 the tension for a given change in length. And then if it's stretched 20 centimeters, well, that's stretched 3 1/3 times as much as the 6 centimeters you have here. You would end up with the following proportions. Okay, this gives you a 20 Newton force for these this length, this stretch, and this cross-sectional area. The ratio of cross-sectional areas is 40 millimeters squared to 10 square millimeters squared, 40 to 1. Okay, that would tend to increase the force. So you'd have 40 times as much force, all other things being equal. But this thing is 3/18 as long, okay? And 3/18 is, 50/3, 16 2/3 times as long. And the longer it is, the less the given change in length is going to affect tension. Okay. Then over here, we have the 20 centimeters over 6 centimeters. Well, this thing is stretched 20 centimeters, where this is only stretched 6. So you would tend to get 26 as much force. Okay, so you tend to get 40 times as much force because of the cross-sectional areas, about 1/16 as much force due to the increased length, and 26 or about a little over 3 times the force due to the increased stretch. So you put all these together and you multiply them out, and you find that the 144 newtons, that's a class conjecture, seems fairly plausible. Okay. From the numbers, it's like you have 40 times here, 3 1/3 times here. That gives you a factor of like 130 times as much force. But now you have only 1/16 of that. Okay, and 1/16 of that is like 8 times the force, and that's not right. Oh yeah, 8 times 20 newtons would be 160 newtons. Those are ballpark calculations, so that's reasonable. So again, you run these numbers, it's plausible. So I expect that class reasoned this out right. Let's see if we can figure out from what's on the board, just what they reasoned out. Okay, well, I think the reasoning here, 20 centimeters over 300 centimeters, that's at 0.06, and it's not 0.06%, it's 0.066%. And they identified that as the strength. Well, that's the ratio of how much it was stretched to how long it was to start with. So that's a good calculation, 6% or 0.06. Of course, the calculation we're going to use for 0.06. It's convenient to think in terms of percents because kind of used to being able to think in percents. Okay. So there's our strain. And what else did they do? Somewhere they probably calculated stress. Well, they didn't calculate the stress because they're looking for the tension. They used the strain and they divided it. The force by the 40 square millimeters. No, that's how they got constant. Okay, right there's how they got 6 newtons per square millimeter. So, okay, well, here we have it. Okay, that's the force. And I don't know whether they used an M there, but that's okay. Force in newtons. I would just call that tension over the 400 square millimeters. Okay, I had to write that C right there. A little careless, I used 40 instead of 400. So there's a stress divided by the strain should equal this. The stress divided by strain should always equal this, and you get this calculation. Okay, well, that's the idea of Young's modulus. Then I asked them to put those ideas together to relate Young's modulus, cross-sectional area, length, change in length, and tension. They said, well, okay, that's easy. Young's modulus is going to be stress, tension per unit of cross-sectional area. You want to understand that quantity. Just visualize tension distributed over the cross-sectional area. Every little fiber in that thing exerts tension in this area. So the tension is proportional to the total cross-sectional area. And then over the percent change in length, if you wish, or the proportional change in length. And we call, of course, we call that the strength. And then you can do the arithmetic and get this relationship. So if you want to solve for tension, you have it. And it's not just a formula. You see right here, the delta L over L is your strength, proportional change in the length, and y times cross-sectional area. Well, you might want to think about what that means. You might want to think then about what it means to solve this thing for change in length. Okay. Change in length would be tension times the length divided by y times cross-sectional area. Maybe not y times cross-sectional area. Ponder what that means. And why we use this calculation. Now you see again, you also have tension per unit cross-sectional area. There's your stress. Identify those things. Think about them until it becomes as intuitive as possible in a reasonable amount of time. Because the more intuitive you are with this, the better you're going to be at using it, and the better you're going to be at solving problems that are related to this. Now, another thing is, we've got this quantity with Young's modulus. Actually, this is 6 newtons per square millimeter. We want to express this in metric units. Well, here we had a conjecture, 1,000th of the 6 newtons per square millimeter. Well, that's actually kind of ridiculous if you think about it. It's 0.006 newtons per square meter. And that means an elastic band 1 meter wide and 1 meter high thickness would exert 1/1000th force of this small. So obviously we're going in the wrong direction. That is okay, multiplied by 1,000. Well, no, not quite, because there's more than 1,000 square millimeters in a square meter. Okay, divide up the square meter into square centimeters, you have a picture much like this. 10 by 10, you have 100 square centimeters. Okay, and then you have I said that wrong. I said divide a meter square into centimeter squares. You're going to have 100 by 100. Okay, and that's going to be 10,000 1 centimeter squares. And each 1 centimeter square will be 100 millimeter squares. 100 times 100,000 is a million. Or you could say take up the whole meter and divide it into millimeters. You're going to have 1,000 this way, 1,000 this way. 1,000 times 1,000 is a million. And people had to stop and think about what 1,000 times 1,000 was, which means that probably overuse of calculators or other distractions bypass the natural fascination most kids have with big numbers. If you haven't thought through that 1,000 times 1,000 is a million, times 1,000 is a billion, times 1,000 is a trillion, and so forth and so on, all the way up to the zillions and bazillions and all that stuff. You haven't. Okay, well, maybe. So you conclude that there are 1 million of these in one of these. So this number has to be 1 million times this, not 1,000 of it. Meaning that you have, instead of 6 newtons per millimeter squared, well, it's the same thing to say you have 6 meganewtons, mega meaning billion, you have to understand mega and giga and so forth. Mega newtons per square meter. Sorry. Then that's actually kind of reasonable when you realize that, and I looked this up, and it was in the giganewtons, wasn't sure how many could have. I stopped stretching steel bars when I got a little older. I wasn't strong enough anymore. to really feel the stretch. Okay. Steel. Ballpark 200 giganewtons per square meter. Depends on the kind of steel, stainless steel, whatever, carbon steel. Okay, what's that G stand for? Hell, one of the questions is gazillion. Yeah, 200 gazillion newtons per square meter. Actually means giganewtons, means billions of newtons. A giganewton is 1,000 meganewtons. So this is 200,000 times as big as this. And of course, you understand that a steel rod of the same dimensions as this elastic stuff wouldn't stretch nearly as easily. Okay. And maybe it only stretches 1/30,000th as far. And actually, that would be the case. I will caution you don't have a constant Young's modulus on that elastic band. It's not a linear force versus length type thing. So you want to be careful about that. Still, right there it is. Okay, that's what you need to know. And think about what it would take to stretch out, let's say, just a thin steel wire, 10 meters long, okay, about 30 feet. Could you stretch it? Could you stretch it a visible amount? What would it take to stretch it a visible amount? How would you measure if you'd stretch that amount? Because it's going to be a little bit hard to see. It might be an invisible stretch, but maybe still measurable. Okay, well, take it from there and ponder the meanings of these things and try to make this as intuitive as possible.